Quantum mechanics is an extremely successful theory, but at the same time, notoriously hard to understand. To get to the heart of quantum mechanics, it is sometimes better to be abstract and formulate axiomatically, a technique commonly used by philosophers and mathematicians. In this video, we have devised a simple analogy that mirrors the three fundamental principles of quantum mechanics. The analogy is with a play with actors, an arena, the script, and audiences. We will go into details soon. Here is a quick summary. The first principle of quantum mechanics tells us that we can represent every quantum system by complex vectors. Why complex numbers? Because we need it to explain interference patterns. These quantum systems are actors in our play, and the Hilbert space is the arena. In every play, actors move and act based on a script. The script is mathematically just a matrix that transforms these initial vectors into final vectors. The second principle of quantum mechanics tells how the quantum system evolves in time. The last third principle tells what happens when the scientist looks at the quantum system. In our analogy, the scientist is the audience of the play. Arena and actors. Everything needs a place to stand, and so does the quantum system. The first principle of quantum mechanics does exactly that. It says we can describe every quantum system by a complex vector. These complex vectors live in some fancy mathematical arena called Hilbert space. Quantum mechanics doesn't tell you exactly the vector for some physical system. Figuring that out for a specific system is a difficult problem for which physicists have developed many intricate and beautiful rules. For example, the wonderful theory of quantum electrodynamics describes how atoms and light interact. Quantum mechanics doesn't specify what the vectors for atoms and light are, it just says that they should be complex vectors in Hilbert space. Abstractly, you can compare this principle with the concept of a bit in a computer. The idea of the bit is independent of the physical substrate which encodes it. A computer can be made of marbles rolling on slides, hydraulic pipes, domino chains, or electric circuits. Similarly, quantum mechanics also doesn't give you a detail of a quantum system. Rather, it says what its structure should be. Let's go through an example. We have a quantum actor obeying the rules of quantum mechanics. In our day-to-day reality, our actor can either be up on the table or down on the floor, which we can indicate by 0 and 1 respectively. However, in quantum mechanics, our actors are described by a complex vector. You can add two vectors to get a new vector and obtain another valid quantum state. Scientists call this phenomenon quantum superposition. We can interpret it as our actor being both up and down simultaneously. Quantum superposition is a fundamental part of quantum computing. In quantum computing, instead of using 0 and 1 separately, we can use both 0 and 1 simultaneously and gain computational advantages. Script. Suppose our quantum actor was down on a floor, and now he is up and down at the same time. This feels like all kinds of classical scripts happening simultaneously. How in the world are we going to explain this? This brings us to the second principle of quantum mechanics. The second principle is basically a script that tells what our quantum actors should do in the arena. This mysterious script is a matrix you might remember from your math lecture. The first principle tells us that a vector completely describes our quantum actors. The natural object that can change these vectors is a matrix, and the correct matrix in quantum mechanics is a unitary matrix. We need a unitary matrix to preserve probability and account for the fact that we might have complex vectors. Just as quantum mechanics does not tell us the quantum state of a particular quantum system, it does not tell us which unitary matrices describe real-world quantum dynamics. Quantum mechanics merely assures us that the evolution of any closed quantum system may be described in such a way. A more refined version of this postulate is basically a Schrödinger equation. In general, figuring out the script of a quantum play is a very difficult problem. Much of the 20th century physics has been concerned with this problem, which requires substantial input from experiments in order to be answered. Audiences. Finally, let's talk about the audiences of a quantum play. Audiences are classical observers who will see the actors up or down, not both places at the same time. Therefore, audiences can only have limited information about what is happening. This is a third principle of quantum mechanics, a version of Heisenberg's uncertainty principle. This principle tells us what information the external observer can obtain about a quantum system. These observers can never precisely tell where the actors will be. Rather, they can only give a probabilistic answer. To be precise, if you have an actor in a state A0 plus B1, then audiences will see the actor in a 0 state with probability A squared and in 1 state with probability B squared. These mind-boggling aspects of Principle 3 are the subject of the infamous quantum measurement problem. Example. So far, we have been a bit abstract with our formalism. Let's see an example of quantum dynamics and compare it with our quantum play analogy. The actor is in the atom's energy level, which can be in a ground or excited state. As they are quantum actors, they are also allowed to be in both ground and excited states at the same time. Now we need a script that tells how our actors should move. In the case of an atom's energy level can change by interaction with electromagnetic waves. When this wave is set with proper frequency, the atom changes its energy level from a ground state to an excited state or to a superposition state. Now comes the audience, who are finally observing the energy levels. When the audience observes it, only one of the two states is detected randomly with some probability. If the atom's state is measured many times and averaged, the atom's energy level oscillates between the ground and excited state. This oscillation is called Rabi oscillation. Conclusion. In conclusion, we have quantum actors whose act is described by a quantum script where all things happen simultaneously. Unfortunately, the audience cannot experience the full richness of a play. Rather, they are limited by Heisenberg's strict rule. So far, our discussion was for a closed system. In a closed system, actors are inside a closed box and observers are outside. What happens if audiences themselves are a quantum system and therefore a part of the play? That is a story for next time.